Embedded systems will evolve during their lifetime through software updates, system extensions, or component replacement. Use of shared resources can lead to violation of timing constraints in real-time systems. In this demo, we will present the possible effects of unverified system changes. The central element of the demonstrator is a beam which is mounted movable at both ends on the surrounding frame. Both ends can be moved independently by separate stepper motors. A user-controlled application controls the position of the right end of the beam. A distributed control application is added to the system to keep the ball in the center position by controlling the left end of the beam. The control application is composed of a sensor task and a motor task that communicate over the CAN bus. When a third application is added to the system, the jitter on the CAN bus becomes excessively high, causing violation of the control loop timing. Let's see whether this can be a problem in practice. Observe how the right end can be controlled by the user. The distributed control application is loaded and balances the ball. Now, the third application, which causes bursty traffic on the CAN bus, is started. The extra load causes violation of the timing constraints of the control application. Observe how the controller starts to oscillate. How can we protect the system from such infeasible updates? We propose dynamic online performance verification, which performs a model-based system-level verification on the system itself. We enrich a heterogeneous networked embedded system with a runtime environment. Our RTE performs a model-based performance analysis, sets execution parameters based on the model, supervises adherence of the applications to their model, and optimizes the system configuration based on model information. All local RTE instances cooperate to perform their tasks distributedly on a system level. Let's take a look at the system model. Software tasks are characterized by their activation period, worst-case execution time, jitter, and their communication requirements. Communication on physical communication media is modeled as tasks. Each RTE is capable of analyzing one or more processors or communication media. The distributed analysis is capable of calculating end-to-end latencies along specified paths. The analysis core on the left controller analyzes the left controller and the CAN bus. The right controller only analyzes itself. The user-controlled application resides solely on the right controller. Its timing behavior is specified and known to the analysis core on the right controller. The control application is inserted into the system to compensate the user-controlled disturbance. The application is composed of a sensor and a control task that communicate over the CAN bus. A distributed timing analysis is performed. All temporal constraints are met, and thus the application is admitted to the system. The third application with high priorities is to be inserted into the system. The analysis recognizes that the new application would cause the control application to fail its latency constraint. Thus, the new application is rejected. Let's see the dynamic online performance verification in action. Again, the right end is user-controlled. The boards indicate their analysis status via the attached LCDs. While an analysis is running, a yellow LED is switched on. The control application is loaded, analyzed, and accepted. The left motor will keep the ball balanced. Now we try to add the third application. The analysis recognizes the violation of a timing constraint and rejects the third application, preventing it from executing. The hazardous update is signaled by the flashing light. As you can see, the system is still functional. This presentation was brought to you by the Institute of Computer and Network Engineering of the Technical University Braunschweig. Please also visit our website at www.ida.ing.tu-bs.de/organic.